So we have a rush job. We need to make this shaft. This part is basically destroyed. The key is destroyed, and we have a wear on this diameter that goes into gearbox. Okay, 1, 2, 3, 4 precision fits. Nothing really special, but we will make this between centers. Rough it out just using the 3-jar chuck. Hold it between centers and finish this part. After that, flip it and finish the other side. Okay, for the steel I will use 1045 steel because that is what I have for now in stock. I don't have 4140 with the commercial heat treat over 80 millimeters and under 150 millimeters. This is 85 millimeter nominal here. So I don't have it, and I won't rough from 160 millimeters just to make this shaft. Okay, so we make it in 1045 and see how it holds up, and we'll probably make it out of 4140 or another shaft from 1045 and send it out for plasma night riding. Okay, let's see how we make this shaft. So I just holded the part in a chuck, didn't face it, just put a center drill and then put a live centered and start to roughing. For now it's like 400 RPM and 0.35 millimeters per rev for roughing. I played with a little bit of feeds and speeds, but 1045 is a very forgiving steel and you can rough it very easily. I could have gone faster, but I decided that I am not in that rush. Now you see me holding my hand on the wheel on the tailstock because many times if you rough pretty hard, the material can slip, especially if it's a ground stock, it can slip. I will always hold my hand when I do roughing, and you see it quite quickly that you can tension the tailstock, and then it had slip and you need to stop. This is like 500 RPM and 0.35. This is the semi-finishing. Now I flip the part and rough the front register. After this I will put a center drill, flip the part and machine the shoulder to length. And all the measurements will be made from the shoulder. Very important when you do this kind of part is that you first do the roughing and after that you do the finish machining, because material have stress in them and they will move, and if it's cold rolled steel, it's move a lot. I had parts move like 1 millimeter just between roughing and finishing. So it is a very, very bad practice to machine, for example, this part and finish it, and after that roughing this part and finish it, and roughing that part and finish it. Even if you rough this part and finish it, after that you flip it and you machine this part, regardless of how you can make it to be concentric again. For example, use a 4-jaw or a collar chuck. This will be not concentric with this, but not how you choose the work holding. I don't talk about the indicating errors. I talk about the errors in stress in material. So it could move, but not from indicating standpoint. just because the material has stress in them. So all dimensions are in 3 millimeters, except the flange. This flange is in 1 millimeter till final size. Now we turn it between centers and finish this shaft. So you can have precision fits and have a straight shaft and not turning it between centers. For example, this shaft I have turned a couple of months ago. It is a pretty long and skinny shaft. It is like 700 millimeters long with 4 precision fits. This fit 1 bearing. This is loose tolerance. Precision fit. Here is a bearing, but it's all chewed up, and another fit. So this I did. I had a longer piece of bar stock and chuck it in the lathe like this, and rough it out, and after that finishing from left to right, and here from right to left. And after that I have bandsawed it off, and that's it. Because in this case, the precision is from this shoulder to this snap ring groove. The overall length is not important. So I just bandsawed it off and put a chamfer, and that's it for this end. And this end is normal turning and chamfer. So you can do precision parts without turning it between centers, but you lose that amount of material. Sometimes it's better to do it like this, but in this case I will turn this shaft between centers and flip it and do it like this in this case. This is how I machined the skinny shaft. I found this video. It's not quite skinny, it's like 55 millimeters in the larger section. Back to our project for today. I finished machining the nose. Now I machined the bearing fits. Between the bearings that is a minus tolerance, so the bearing can slide back easily. Now I machine this skinny part, and I noticed that I have some taper, and I want to fix that. And this is how I indicate the part in to remove the taper. Okay, you just saw me how I adjusted the taper. In the last year, the taper grew on me, and it's time to adjust. I put 2 indicators. I had the difference from here to here, roughly 0.12 millimeters. So the difference must be a radius, like 0.06 millimeters. This was smaller, so this must go that side, because you don't need to cut that much material on this side, which is smaller. Always the smaller part, you move it away from the cut. Another important thing is the tightening of the blocking knob on the quill. If you tighten it more or less, it will affect the straightness. So for example, now I have, it's under my mark. I loosen it up. It moved like 0.01 millimeters. If I tighten it harder, it moved like 0.002 millimeters. So this also affects the taper while you cutting. Another factor that affects the taper is the life center. If you use a long life center or a shorter life center, this also can affect the taper of the machine, because no machine is perfect, and you need to work around it. So now I need to adjust a little bit more, and this part would be done. Now we are at the milling machine. I found the center. After that I do roughing with a 6mm end mill, full depth, in 2 passes basically. And after that I will go with a reground 8mm end mill. It is like 7.7, and make basically the slot and do like 1 or 2 passes to move it over and to obtain the perfect fit. And it works well. And we are at another milling machine to drill the holes in the flange. The shaft is longer than my Z-travel, so I need to stick it out. I just use the chuck and 1 to 3 blocks to block the shaft up near the flange, so we know that we are pretty straight. It's an M8 thread, so not crazy precise. And this is how it looks closer, just the chuck overhang from the table and the 1 to 3 blocks blocking it up. Now I face the shaft to length, because this was the saw cut, where I put in the first center drill. If you remember, it was a long shaft, and now I drill and tap it. So the shaft is finished. We are in tolerance. All turned out very good. The bearing fit is plus 0.02 millimeters larger than nominal. This bearing fit is minus 0.1 millimeter smaller than nominal, because here come 2 tapered roller bearings, and this must slide to pretension those tapered roller bearings. Here is 0.01 millimeters under nominal to be able to slide in the gearbox, M10 screw to hold it in the gearbox. In the front we have 2 bolt hole circle patterns. We have 3 that are from center to center like this, 50 millimeters, and the other from center to center, 60 millimeters. So they are not on a radius pattern, but I have drew up in CAD and calculated what the bolt pattern is, and that is what I have written in my DRO, so we can use the bolt hole circle to drill the 3 holes in one setup and then other 3 holes in the other setup. And we are pretty close. Those are M8 threads, so nothing real precision in those threads. This is the part done. Goodbye.